Okay, another example. We'll build ourselves up. Again, if the acceleration is constant, we can either use the definition straight away, or we can use the derived constant acceleration equations. It could be a ramp, it could be a car, it could be a boat, we said a plane, it could be anything, or it could be a projectile where the air resistance is negligible, no good for feathers, and no propulsion, no wings. So here's another process, though, that's interesting, and let's just lay this out. So suppose rather than dropping it, I throw it. Now realize that I could throw it down, so there's part of the process here, and this is key, so visualize this. Really think, this is me pushing it. And we'll see that pushes cause acceleration, but me pushing it. Once I let go, then this applies. But while I'm pushing it, I either am not interested in that part of the process to analyze, or I can be. But I need enough data to measure myself or to be given. So let's fit it all into this, and rather than dropping it, we're going to throw the object up, not to be misinterpreted. Okay, so here we go, and we're going to toss it up. And let's see this process. So let's go ahead and do it. So rather than quick read a problem, let's look at this process here. We have the meter stick, and rather than just dropping it and having free fall, I could throw it. Now I could look, once I let go, it's free fall, free flight. But what I'm going to do is throw it. I don't know, let's see, how far do I want? You know, you could throw it, you could, however, whatever distance. Last semester I speared a poodle with a javelin. I don't know what I'll do this semester. Not really. Uh-oh, now I'm in trouble. So I'm going to throw it. Now this starts at 0 and this goes to 30 centimeters. I just committed a mortal sin. 30 centimeters. What exactly do you mean? Let's see. 30 centimeters. I don't know what that means. Again, as you guys know, it's either 3.0 times 10 centimeters. It's 3 times 10 centimeters. Right? I don't know which one it is. It's either 1 sig fig or 2. So this one's pretty good. I would say it's 3.00 centimeters. If I used a vernier caliper, I'd say it's 3. If I just know it to within a centimeter, and I say this for millimeters, right? Okay, let's do this. Let's throw our brains. Here we go. I'm going to toss the brain, and I'm going to go like this, and let's see what we could measure, whatever, we'll lay it out. See anything implied? What's the implied information? Then I go like this. Okay. Not exactly 1D, but kind of. Do it again. Let's go to 30 or 31 or 30.1 or whatever I've got. Put that down there to grab my hand. Start here. And all right, so questions that you could have, like how high did it go? You could measure it or you can calculate it. How long did it take? How fast did it leave my hand? What was the acceleration while in my hand? Kinematics. Time instant, time interval. Position, change in position, displacement. Distance, velocity instant, average velocity, acceleration. That's kinematics. So we just go through our mental checklist and get good. What do I need to do? I need to visualize and sketch this process. So let's do it. All right, I'm going to do that right here. And let's see what I've got. I've got, and I'm going to slow it down in my mind. Surfaces we often draw like that. And I'm going to draw this thing and see what I've got here. I got a blue brain. There we are. And I'm going to release it at some place. Not the darkest color, so I'll go purple. Some place which I called or set to be 0. I need my moments, so that's moment 1, and I'll set that y1 equal to 0. That's where I started it. And then I pushed it up. Now my hand stopped, but the brain kept on going. So, what do I know? Well, it's got some velocity, v2, at state 2, or moment 2. It's got some y2, which maybe I measured, and I did. It's 30 centimeters, but I think it's good to within a tenth of a millimeter. Maybe. Again, make a call. And then what happens? And then it goes up. We'll model it as going up straight to what I'll call state 3 for the top. All right, cool. That's the process. And then it's at some, I don't know, y3. So what have I done? I've done my states, 1, 2, 3. Maybe I want in between. Then fine, put it in there. My coordinates I need. In this case, I like to call up positive. It's going up. Even if it ends up coming down, if it goes up, I call it positive. Next to the coordinates, we're going to see as we go on that it's really useful to say that the acceleration in the y direction is down, which now means negative, for the value of g. Now, I can use that from 1 to 2, or 1 to 3, can I? Can I use acceleration as g from here to here? No, right? The only time it's in free flight is here. Now from here to here, right, because I'm slowing down, so I've got an acceleration this way. I'm decreasing my speed, so the acceleration's opposite. Here, I'm increasing my speed, so here. I don't want to have the same variable, so I could say A2 to 3. Or A2 to 3 is a constant down g. So this is where this really, going ahead is going to be all messed up because you get messed up here. Here, the acceleration's up due to my hand. Let's get rid of this guy here. So in this case, I don't know what it is. A1 to 2 equals the acceleration of my hand. And we're going to model that as a constant acceleration. It's probably not the way muscles work, and you can look at that and whatever. One thing we can certainly do, though, is to define acceleration average as a change in velocity here from 1 to 2. So that's from 1 to 2 over the time. So now it's getting a little more complicated. There's more puzzle pieces. It's not a 100-piece puzzle, it's a 1,000-piece puzzle. Fine. Just take it slowly and build your speed. I don't know where it's going to go. That's the good puzzles. Now, I don't know how it's going to work out. What do I know? I don't know what I know. Well, I know this. This is a lot already. From 1 to 2, I go here, pushing with my hand, giving an upward acceleration. Then I release it, and then it goes to the top. I've got my coordinates clearly. In both cases, I'm calling up positive, but the acceleration is different on the different intervals. And so what other information do I know? I don't know. Let's see. What am I given? I guess I'm given y1 is equal to, and I guess I'm given y2 is equal to. What else am I? What's implied? I think it's what's implied is that I start from rest. v1 equals 0, so put that in there. And the other thing that's implied is if you go to the highest you are, then you know that is implied v3 is equal to 0. So that's implied. Okay. And the other implied information that I wrote up here is that A from 2 to 3 is down, which I called negative, g. That's all implied in the wording. Okay. So how do I do this problem? Well, I haven't said exactly what I know and want, so I just put that in, whatever I measured, and look for whatever. The approach here, again, is going to be the general. I would say either the definitions always work, or in this case, yes, a constant acceleration, at least modeled. And then the general equations are the good old friends now that you can write in 30 seconds. Try to be able to write that in 30 seconds. With the subscripts, all subscripts, you can do it. Then I make it specific. And so in this problem, the difference is that in this problem, I mean, this is the key. Visualizing this is it. And then you go, what tools? You don't have to invent new tools. Oh, all right, here's my tools. You know, you will have to have been given more information, so don't worry about how exactly you solve it. But there's the tools. Let me make it specific. So making it specific, I'm going to go from 1 to 2, where acceleration, 1 to 2, is equal to up, or positive. I don't know. I could also call it AH for hand. Okay, and then I go like this. Delta y, 1 to 2, is equal to V1, delta t, 1 to 2, plus 1/2 A hand, delta t, 1 to 2, squared. Up. That's cool. V2 is equal to V1, that's 0, plus A hand, delta t, 1 to 2. V2 squared, not a new equation, but useful to avoid some algebra. V1 squared, oh, wait a minute, okay. 2A hand, delta y, what? 1 to 2. Now I'm not, it just saves me time. Otherwise, there's too much in your brain is going to short circuit and you get lost on the simplest things, which we do all the time. Okay, cool. So I'm going to do that. How am I going to do it? I don't know. I'll just do the math now. Next, what do I do? The last thing I do here is, in this process, I've got 2 to 3. In that case, acceleration, I know 2 to 3 is negative or downward g. And so I'm specifically fitting these general equations. Again, this could be a car that speeds up and slows down. Anything that speeds, going up a ramp. You push it, speed it up, and then it slows down. Whatever. Or vice versa. It could speed up and then hit some plunger and slow down. And you just break it up this way. If the acceleration is constant the whole time, I can relate any earlier state to any later state, make it easy, choose wisely, fine. If the acceleration changes, well then I'm going to have to break it up. And then I'll just go. Delta y, 2 to 3 is v earlier, which is v2. Delta t, 2 to 3, plus, wait a minute, that's that. So I'm going to make it specific. Minus 1/2 g. I put that in for a. Delta t, 2 to 3, squared. Oops, squared. V3, v later, is equal to v earlier. Minus g, because that's the acceleration here, delta t, 2 to 3. Or v3 squared is equal to v2 squared. Minus 2g, because I put in minus g for the a, delta y. Which delta y? 2 to 3. Where is 2 to 3? Ah, I didn't put that on here. That's my delta y 2 to 3, and that's my delta y 1 to 2. Now I know what I mean. You do this, you are going to the head of the class. And then solve. I don't know. What do I know? I don't know what I know. I'll have to be given more information than I have here. Either have to measure it or be given it in a problem. Okay? And again, you do have always V average is equal to, in this case, to be V3 or V2 plus V3. It doesn't matter which order you write it over 2. But, and then check it off and go for it, and you're good to go. So any kind of problem that you can model this way. Now the truth is, often we don't go abruptly from one acceleration to another. I guess we can. You know, there's sometimes a gradual transition. I walk, I don't just stop, I slow down. So I can walk with no acceleration. Then I can decelerate, which is an acceleration, and stop. And then I can speed up more rapidly, or so whatever. I don't know. Don't overthink the processes, because that's solving. So lay it out. Try to interpret the words. Sometimes they're a little bit ambiguous, and you just have to ask. And sometimes we write it, and we know what we're talking about, and we haven't actually said something clearly. So this is going to do it. And when we do 2 dimensions, we're just going to do the horizontal motion separate from the vertical, or the along the plane motion separate from the perpendicular to the plane motion. It's the same thing, but now we need vectors. So we'll be going into vectors. I think we're good to go.